Hello. I have my first viewer. The YouTube live will begin pretty soon. I'm just waiting for people to come join us and just put the URL up. So I'm going to give it a few minutes while we wait. Welcome everyone who's made it here so quickly. Great job. I'm going to open up our first poll, which is just our check-in about who's here. And feel free to add your name to the word cloud right there about who's here, and you can see who's here in the poll results on the Canvas page. Hi, Cody. I see you. Hi, Dreama. Hi, Katrina. Hi, MK. Hi, Sunny. Hi, Joe. Welcome. Hi, Marisa. Thanks for joining us. I'm going to give that a couple more minutes because I know it might take that long for people to get in here. So feel free to get yourself a snack or a drink or whatever, and we'll get started in a little bit. Meanwhile, just like I said before on the Zooms, you can view your concept quiz already. So if you haven't taken a look at that, don't be scared. You can click on that concept quiz and then you can click out of it without having responded to any of them. So you can see what all the questions are. And if you want more clarification on a certain concept that speaks to that quiz, here's a great place to add in your questions. Hi, Rihanna. Also, now is a good time to just kind of set up your screens. That's what I'm doing here. I know that this is a little bit challenging because you kind of have like 3 different things going on. You're going to have a screen where I'm speaking to you on the live screen. I would also recommend popping out a separate window where you've got the Canvas page up so that you can see the results coming in. And then you might want to have a third window down at the bottom where you're responding to the polls. So it's kind of a 3-window setup, and that's what I'm doing right now is I've got 3 windows open, one for the stream, one for the poll responses, and one for the poll results on Canvas. And I'm trying to set all 3 of those up in a way that I can view them all at the same time on my computer. Easier said than done, but go ahead and work on that if you'd like to while we continue to wait for others to join us here. Welcome, Jesse and Nick and Avery. I'll put my name into the word cloud too. There's Melissa joining us, and just a couple more minutes before we move on. Ooh, I bet you're wondering what temperature it is in here today. Let's take a look. Oh, it's a little bit warmer. Last time I was with you, it was 38 degrees. This time we've got it at a balmy 47 degrees. Yeah, it actually 47 is a lot better than 38. So that's good. That's good. Hopefully the markers won't stick to the board then. Gotta find the markers. I'll be looking around for my markers and stuff while we wait. Uh-oh. Kind of running out of ink. All right, I'm just making sure that there's ink in the pens. Okay, we're ready to learn. So we've got 14 people in the word cloud so far, and we've got 14 viewers, so welcome. I'm so glad that you could all make it here. And as we wait for some more to possibly join us, thanks for the thumbs up, I've got a couple quiz prep questions, and that's just a fun way for us to practice out some of the things that are on the concept quiz. Like I was saying before, you can open the concept quiz and not have to respond to the answers. The due date is tonight at 11:59 p.m., but you can certainly pop in and out of there and scroll through all the questions. Hopefully there's no surprises on there. I really did read all of your discussion posts that you posted yesterday to the concept discussions, and I used that to inform the quiz. Feedback, that's the name of the game, isn't it? So welcome to one more person just joined us. The names are flying around, so I'm not sure who just joined us, but welcome everybody. And I think that now to get us started, I'll move on to our first warm-up question. It's a quiz prep question, and it's a clickable image. So it's gonna say, plot a point where Java is really sad and Rancor is just a little bit happy in the state space. State space was one of our big concepts this week, and I'm going to turn that question on now, but what I'm going to do for a second is for just a second here, I'm going to shut off the show responses because I don't want people to just work off of what they see others doing. I want everybody to give their own response. And so go ahead and click what you feel is your answer to the question. Here's a state space. Here's an X and Y state space. Java is X. And remember that negative numbers denote sadness and positive numbers denote happiness. So click on a place in the state space where you think it represents Java being really sad and Rancor being just a little bit happy. Right now on the results page, you can see that we have 6 results so far. And knowing that there's about 15 people watching, I'm going to wait till that gets a little bit closer to the number of watches. And then I'm going to put the responses up. I have the responses hidden right now purposefully because I don't want you to just look at what others did and then click that. I kind of want to just consult the cloud all at once. And so I'm going to put that on there a second. I have 12 responses so far, so if anybody else wants to go ahead and click, you don't have to be right. This isn't getting graded or anything. It's just kind of a fun little game for us to play. And so we got 13 responses, and maybe we can get just one more. We still have 14 viewers, 15 viewers. That's great. And then I'll show the responses. Oh, somebody just took theirs back. Change your mind. If you change your mind, that's perfectly fine. You should be able to erase your answer and then replace it with something else. Hopefully I have it set on that. Let's check it out. Let's see what people are responding. Yeah, right. So we're talking about Java as X is really sad. And so you see that people are responding with the X in the really negative area. And then Rancor is a little bit happy. And so that would be a positive value of Y. And that positive value of Y is it's a little bit up in the Y, but it's not super high up in the Y. And so I've got all your responses in the second quadrant. That's exactly what I'm looking for. And you're going to see a similar question on the concept quiz that gives you some situation. It's not exactly the situation, but it's some kind of Java and Rancor situation. And then it says which XY point represents that. So that's not a visual in the quiz. It's more of like a text form. But trying to translate your answers into a text form, I would say that you're going to have a large negative number for the first component, for the X component, and then you're going to have a small positive number for the Y component. Way to go! Hopefully you're having fun with that. Let's move on and do just one more quiz prep, and then we'll go into start to answer your questions, whatever questions you want to see about the homework. The next one is going to be a multiple choice. This is, again, similar to a quiz question that I have, and it says, which equation shows negative feedback? Again, I'm going to hide the responses for just a second so that people aren't just trying to work off what others are saying. But I've got the results shown up there. And so go on and look at this next poll, which says, which one shows negative feedback? Oh, my bad. I didn't want to show the responses yet, so I hid them. Okay, and so go ahead and answer. There's 4 choices of equation there. The first one says x prime is equal to negative 4, or x prime is equal to 3x, x prime is equal to negative 2x, or x prime is equal to 0.1x. Which one of those represents negative feedback? 10 respondents in. I'll wait a little bit more for the other 3 or 4 people if they want to respond too. And now we're up to 11, and I'll just give it another couple seconds. Go ahead and answer whatever you think. Again, it's not going to be graded or anything, but it's going to give me an idea of any misunderstanding there. So, in case some of those answers are kind of like a little bit tricky. And so I'll be happy to clear it up depending on what I see in the results. And let's see the responses. All right. Yeah, see? Tricked ya. That's why I put the x prime is equal to -4. That was actually a trick question, so don't feel bad if you answered that. What's wrong with that answer? Why isn't the answer x equals -4? Because I thought negative numbers counted as negative feedback, right? But they also have to have the x. You see, so the answer of -2x, which is at 85% on this poll, is the correct answer because you have to have a negative number in front of the state variable. In order for there to be feedback at all, there needs to be functional dependence on the state variable in the right-hand side of the differential equation. And I see somebody adding in the chat that there's no state variable in x prime is equal to -4. That's exactly right. The reason that x prime is equal to -4 is not the correct answer, it's a trick, is because it doesn't have x. And so if I had the state equation or differential equation x prime is equal to -4, that would be no feedback. There's no feedback at all because there's no x. Even though there's a negative number, -4, there's no x there. Yeah, great. So I think that's starting to clear up some misunderstandings, and that's exactly what this is all about. I also saw somebody respond with x prime is equal to -0.1x, and I was kind of thinking that would be a little bit tricky too, because that's a number that's like less than 1. It's like a decimal, 0.1 times x. But that, again, that's not the right answer either. Even though the coefficient is 0.1, it's a positive 0.1, and so that would represent positive feedback. So again, x prime is equal to 3x and x prime is equal to 0.1x, both represent positive feedback. X prime is equal to -4 represents no feedback, and x prime is equal to -2x represents negative feedback. Cool. So we're all getting a little bit warmed up here. Let's see. So somebody, just so you all know, there is one chat function available, but it's only available to people who have logged into YouTube. There's not an active chat mechanism for me to do through the live polls. The closest thing to a chat that I can do on a live poll is going to be to open up an open-ended scrolling poll. And there will be some of those, as you can see on my plan on Canvas, there are some of those folded in so that we can try to have a conversation. But unfortunately, there's not actually like a chat function on the Poll Everywhere software. What I'm seeing here is that there's a couple people who are present on the live chat on the side of my YouTube live, and that's because those people have logged in through YouTube or Gmail, and those people are asking if there's another chat board somewhere else, and there's no other chat board. I wish there was an easy way to incorporate a chat into this, and I think that since we all have 3 screens going already, the easiest solution there would be to ask you to log in through YouTube. If you have a Gmail account or a Google account, that's the same thing. So just log in through there and you'll see that there's a subset of our viewers are having an active chat on the side. It would be great if we could include everyone, but the only way to do that would be for you to log in. Okay, so go ahead and do that if you want to be active on that chat on the side, and I'll be watching that too. But I'm mainly focused on watching the polls because that is the thing that everybody's invited to and didn't have to log in to get to. And so you'll see on our Canvas page that our next question is, what section should we talk about? The goal of this YouTube Live is going to be to capture some exercises and some work on the board. And so I'm going to try to figure out which section you all want me to focus on by activating this next one. So go back to your polls and you'll see that I have one respondent so far for section 1.4, although I have a feeling that's going to be the winner, because as I was warning you earlier in the week, the work in section 1.4 is probably about half of the work for this week. As much as I've assigned exercises in the other sections, 1.4 is really the toughest section. I already received some really valuable feedback on Zoom that people said that they were having trouble and wanted a little elaboration on the chemical kinetic equations in section 1.4. And so while I wait for the rest of the people to answer the poll, I think I will just address that right now because I think people wanted to see that. Does everybody have your book? This book is available for free now as a PDF online. I've shared the link in a Canvas announcement. I'm really excited and thankful that that's now completely available to everyone. Although I will say I have a big preference for the physical copy because that way I can just pull it out anytime. Sometimes I'm cooking dinner, sometimes I'm doing other stuff out in the garden, and I'm just glad I have my book with me here. What I'm going to do is I'm going to open up the next question, which is a brainstorm that says, what exercise from section 1.4 do you want to see? And I'll let that brainstorm kind of bubble up as I, on the board, do some work about chemical kinetic equations. Okay, so I'll just edit this and get that going for you all. So you can see I'm replacing the capital word section in that next question with 1.4 because that's what you've told me you'd like to focus on. And I'm going to make that one go live now. So this next question is in the brainstorm mode. Remember that this mode is really nice because you can vote up or down on anything that's been put in. So go ahead and use that to ask. 1.4.17 is exactly what I was going to do while we're waiting for that brainstorm to bubble up. And so I'm glad to see that pop up first. So I'll take care of you all there by starting to address exercise 1.4.17. I'll probably move on to do 1.4.17, 1.8, and 1.9. I'm going to do the 3 exercises and maybe 22. I'll do probably all 4 exercises that I assigned on pages 36 and 37 here. On the board, those all regard chemical kinetic equations. And so go ahead and, in the brainstorm, go ahead and throw up some other questions that you'd like in addition to these. And I see someone else said modeling change equations, and that's great because that's what we're going to focus on in this section. But if anybody wants to add specific exercises that were assigned that they would like to see done, go ahead and state that really explicitly so that I know exactly what page to turn to and do after I finish 1.4.17 through 20. That's what I'll do first. I think I might make this saved separately as a snippet for later on modeling chemical kinetics. And so I'm going to take my jacket off so I look real professional. All right, this is a video on modeling chemical kinetics. So let's start with a really simple case of a chemical kinetic equation. For example, let's say that we have a molecule A, and that molecule A is being transformed through some chemical process into a different molecule B, and that's occurring at a rate K. All right. What you want to consider here is that the state variables are going to be the concentrations of each chemical. And sorry, I'm still looking at the chat here. Somebody says that on their quiz, can they do part of the quiz and then exit and do the rest? I'm not sure about that. So somebody's asking, can they just respond to half the quiz and then submit it and come back later? I would recommend that you just write down on pencil and paper what you think the answers to are, and then, oh, okay, thanks for responding. Somebody just tried that, and yeah. Okay, so yeah, you can do just some of the quiz and then come back for the rest of the quiz later. Okay, so going back to this situation here, we have the state variables are the concentrations. So the states here are going to be the concentrations of A and B, and we're going to talk about how those concentrations change in time by writing down some state equations. Okay, so because we have two states here, A and B, those are both going to have state equations, or it's going to be a two-dimensional system of differential equations that describes the system. In the book, you're going to see that already laid out for you is the change equation for A prime, and they write that down as minus K multiplied by A. And that's because as the reaction goes forward, the reaction rate is K. But of course, we have to expect that the rate of change there is going to be proportional to how much A there is. Like, I can't just put minus K here, kind of what we were saying before, because if I just put a minus K here, that would mean that there's no feedback. So that would mean that the reaction is happening even if there's zero concentration of A, but that doesn't make any sense. And so really we have to think that the reaction rate is speaking to a constant of proportionality, where really you're going to have a minus K multiplied by the concentration of A, so that if there's a higher concentration of A, the reaction will happen faster, and if there's less A, the reaction will happen slower, and if there's zero A at all, then there can't be any reaction taking place. So the rate of change in A is directly proportional to how much A there is, and it's happening at a rate, proportional rate of change of K, so it's minus KA. The reason that there's a minus is because we're losing A and we're gaining B. And so question 1.4.17 says to use similar reasoning to write the equation for B prime here. Again, this minus means that we're losing the A. How much B are we gaining? Well, every time one A disappears, it turns into one B. So it seems logical that the amount of B that we're gaining is the same as the amount of K that we're losing. But we're gaining it instead of losing it. And so I would say that the equation for B, which is the answer to 1.4.17, B prime is equal to KA, as opposed to here where we have the minus KA because we're losing it. Okay, I'm going to lower the brightness on my screen because it's making a reflection there. Okay, hopefully that's a little bit better. Moving on to the next exercise here, then we have a slightly more complicated equation. This more complicated equation is A plus A goes to B, or it could be expressed as 2A goes to B, again with a rate K. There's a little K above the arrow. And so here we have the simplest thing where we're trading one A for one B. And here it's a little more complicated because now it takes two A's to make a B. Okay? And now if I need two of the A's in order to make a B, what's happening here is that there's a bunch of A's floating around. But in order for this reaction to take place, one A has to meet another A, and they have to be in the same place at the same time. So when I talk about the state equation that describes the rate of change of A, it's not just going to be proportional to the concentration of A, but it's going to be proportional to the concentration of A squared. The reason it's an A squared is because one A molecule floating around needs to meet another A molecule, and they literally have to touch. They have to be in the same place at the same time in order to make that happen. Really, what's underlying this mathematically is a little bit of probability theory. You may have learned in probability theory that the probability of an event A and event B happening at the same time is equal to the probability of A multiplied by the probability of B, okay? So over there in the bubble, I drew a little probabilistic reasoning for why it's an A squared is because if you have two independent events and they both have their own probability of occurring, probability of A, probability of B, if you want them to happen at the same time, that's the same thing as the A meeting the other A and being at the same place in the same time. You have to multiply their probabilities together. That's why I have an A times A there. But you see, I've added a little space here because it's not just going to be that A prime is equal to A squared. When this reaction happens, you're going to be losing the A's and you're going to be gaining the B, okay? So knowing that knowing that my concentration of B is going to change, I've also made a placeholder for that rate of change, which I'll write later. But going back to here, how fast is this happening? Again, it's happening at a rate, a constant of proportionality named by K. Just like we had the K over here multiplying the A, we're going to have the K over here multiplying the A squared. And we're not done just yet. The other thing that you'll see in the book, here I'm referencing page 36 in the book, is that you have a negative sign, but it's not just a -1 like how we had a -1 here. It's a -2. -2K A prime. A squared. So A prime is equal to -2K A squared. That's because we're losing both of the A. See? Over here, we were just losing one A, and so we're -1. We're down by one A. Over here, when this reaction takes place, we're losing 2 of the A. And so we have to say -2K A squared. That might remind you of a little bit of stoichiometry. Remember in those equations where we had to like count up how many of each molecule we had? That's kind of the thing. That's kind of the reason why we have the 2 here. We're losing 2 of the A. But then when we talk about how B is going to change, you can see back over here, what we've done is, since we're trading exactly one A for exactly one B, B's equation for its rate of change mirrors A's, except it changes by a minus sign. So over here, you might think the same thing's going to happen, that the state equation for B should mirror that of A, which it almost does. But the thing is, when we trade 2A, we only get 1B. We don't get 2B. And so there, we're going to have a plus KA squared. Again, the kinetics is going to happen at a rate proportional to the square of the concentration of A, because 2 of those A molecules have to meet each other in order for it to happen. But we're only gaining 1B. So that's why I have a +1 in front of here instead of a +2. And that's the response to 1.4.18. And so this is 1.4.18. Okay, cool. And so if you keep reading on in the book from there, you're going to see that this actually is a great analogy for some of our examples in ecology, like the shark tuna model that I'll start making more videos on for next week. I'll start diving deeper into that shark tuna model, but you can see on page 37, they've written that as kinetic equations there. So that's kind of a fun analogy. And so here it says in exercise 1.4.19, following this analogy, finish writing the change equations for the reaction A plus B goes to C. Oh boy, there's a lot of states in that one. A plus B goes to C means that we have 3 states, so a 3-dimensional state system instead of 2. So I'll erase the board and everybody start to think about 1.4.19 and we'll get the answer to that together. So as we move on to questions number 19 and 20, you're going to see that we're going to write down change equations for a reaction that's just going one way for number 19, and then we're going to fold in the reverse. That was my lights falling down. But the lighting didn't really change, so I guess maybe those lights aren't as necessary as I thought. Anyway, number 20 elaborates on number 19 because it allows reversibility. It allows the reverse of the reaction to occur as well. So let's do both of those on the board with a three-dimensional system where A plus B goes to C. Because we have three concentrations involved, we're going to have three different states, and so we're going to have three different state equations. When you think through these state equations for each one of them, you're going to think about what does it take in order for that reaction to happen. Is it as simple as one thing changing into another, or is there some sort of interaction that needs to take place in order to get that to happen? Oh, somebody's having a harder time reading the board, so maybe my lighting system matters. Let me go pick up the lights. Some lights over there just fell down, so I will try to get that fixed. Okay. I don't know if that helps. Hopefully it does. As usual, thanks for, or maybe it was just your internet. I don't know, but hopefully everybody can see. I'm trying to write as big as possible in hopes that it's readable. Okay, so let's see. Look here. Right, so like it says in the book, they've already given us the reaction, the state equation for A prime, and they've written it as minus K multiplied by A, also multiplied by B. That's because an interaction between A and B needs to occur in order for us to lose an A. So that's why the minus sign is there, because you're losing an A. And also, how fast or slow is that happening? That's spoken to with the reaction rate K. So you throw the K in there in front. Great. So what about B? B seems like it's pretty much the same thing as A, right? Because it's just the other involved in the reaction in order to form a C. And so it's actually going to mirror the state equation for A. It's going to be exactly the same thing, minus K times A times B, because it's the other player involved in the reaction of A plus B. And finally, we want to know what's going to happen to C. So every time we trade one A and one B, we get one C. And so how do you think I'm going to express that? Just by having a positive equivalent of K, A times B. That's right. So it's pretty much trading at the same rate, except that you're gaining a C, and so that's why there's a plus here instead of a minus. Okay. Of course, things would be different if that resulted in like 2 of the C's, then I would have a 2 there or something like that. But because I'm only getting 1 C, that's why there's a +1 coefficient right in front of the rate there. Okay, and so that's the answer to 1.4.19. And then 1.4.20 asks you to do a similar exercise for a reversible reaction. And so this one is reversible. That would mean that A plus B goes to C, and it can also go backwards. So we have two rates, 2 constants of proportionality where we used to have 1. You'll see that in the book. They call those KF and KB. So you have K sub F, which is the forward constant of reaction rate, and then you have K sub B, which is the backward rate. It's still K, which is like the constant of proportionality, how fast or slow is the reaction happening, but because we have a back and forth, we're going to use subscripts to denote that there's a forward rate and then there's a separate backward rate. The K sub F and K sub B are parameters as opposed to variables. Remember, the variables are the states. Those are the things that we are explicitly tracking as changing in time. And those are the things that we define the state equations for. And then other letters, they might be letters or they might be numbers. Other things involved are parameters. And those are the K sub F and K sub B. Okay, so in the book, you'll see that they've already provided us with some of this information. They already provided us with the answer for A prime, but I'll write it a little bit differently than they wrote it, just because I'm explaining it. Because I'm trying to make an extension of this problem. And in this problem, I've already modeled the forward rate. And so I'm just going to copy the forward rate right into here, where I'm going to replace the K from before with a K sub F. That's the same forward reaction rate that I had before. And I might as well fill that in for B too, because I already know that that's what was happening. And I might as well fill that in for C too, because we just went over that, right? And so I'm kind of building it up for the forward reaction for all of them, and then I'll build it up for the backward reaction for all of them. Okay, these equations are the same as those. The only thing I did was replace the K with a K sub F, because now that there's a backward rate, the forward rate is denoted with a subscript of F. Then for the backward rate, we just have to consider how things are happening backwards. So you can see that if the backward reaction happens, then I'm trading one C and I'm getting an A. I'm also getting a B, but when we're focused on the A prime equation, I want to speak to the fact that when that backward reaction happens, I'm gaining one A, and that's at a rate that's proportional to K sub B, and also times by how much C there is, because C is a concentration that dictates if that's going to happen or not. So I'm going to do a plus K sub B multiplied by the concentration of C. Just checking in back with the book on page 37. This is the same equation that you see on page 37 underneath exercise 19, but I just switched it around. I just switched around the terms, but you can do that. It's the same equation. So in number 20, we're trying to write equations for B and C. B is going to be a copy of A, just like we were saying before, because it's acting in the same way. And so that backward equation there provides us with this term where we're producing one single B every time that backwards reaction happens. And also during that backwards reaction, we're going to lose a C. And so the same things that you saw as a positive term in the A prime and B prime equations, it's going to end up as a negative term here. So you're just going to have a minus KB times C there. And that's the answer to 1.4.20. All right, great. I hope that really helps everybody out with those chemical kinetic exercises numbers 17 through 20. And I'm still looking for what other questions you'd like to ask. So I'm going back here, and I see that even though this poll is still live, I don't see anybody else asking me to do any more questions. Are you sure? You can still ask. I can stay here till about 2 o'clock and then I have to cut it off. So I still have a full half an hour. If there's anybody still watching, there's 13 of you still watching. If anybody wants to suggest another exercise, whether it's from 1.4 or 1.3, I saw somebody answer in the previous question, somebody wanted to see from 1.3. Just throw it in there right now and I will answer it. I really want to do what you want me to do. So I'm looking for questions. Someone else says they have no specific questions. That's okay. If nobody else has any questions, I don't have to do any more, but I'm kind of worried that maybe the reason people don't have questions is because I heard a lot of concerns about time management today in the Zoom session, and I'm thinking that maybe people haven't approached the further exercises in 1.4 yet. That might be the reason. And so I'm going to flip to those because I know those are challenging and I want to make sure that there's a resource to help you with those. Okay, so it's totally understandable if you haven't made it to the further exercises of 1.4 yet, but it's Thursday and those are due on Sunday. And I want to make sure that you feel like it's doable in time. So yeah, so somebody here is telling me that they're watching too, but they are actually in 1.3. Okay, so I'll just let this marinate in your head for those who are still watching. If you want to flip through the further exercises in 1.4, I've assigned a lot of those, and those are tricky. So if anybody wants to put in 2 cents on those, I'm happy to do that in a little bit. But I'm going to turn back now to page 21, where someone said that they are starting to work on the vectors and like some explanation of vectors. So I'll erase the board and I'll give a little explanation of vectors. Let's see, where did I put my, oh, there we go. I also have to dry it or else the markers get mixed up. So that's why you see me erasing it twice. What are vectors? They are a multi-dimensional generalization of our concept of a number. Okay, so vectors are a concept that is going to scale up to more than one dimension very nicely, but is a little bit of an on-ramp, a learning process that goes along with it. So I'm really glad that somebody asked a question about vectors. Okay, so that's basically the skinny of what I'm saying here is vectors are a generalization that allows us to take the concept of numbers and then scale it up into higher dimensions. The key thing that I'd like you to understand about vectors is that they, no matter what dimension they're in, they always have 2 very important properties. And that's going to be their length or magnitude and their direction. Okay, so I'm going to focus as we talk about the 2 properties involved. This is what we want to focus on. And this is for no matter what dimension you're in, what we have is a magnitude and we have a direction. Okay, let's start with what we know well, which is one-dimensional numbers and the one-dimensional number line. So in 1D, a 1D vector is just a number. And it lives on a number line here. Here's just 0, so we kind of mark a place so we know where we are. This is just a number line. In the context of what we've been learning, though, consider that this is like a one-dimensional state space. So you've seen a lot of graphs in the book where this is marked as X, and we're talking about one single dimension X changing in time, and that here's the state space for it, okay? Anytime that we have a number in 1D, If it's a positive number, it's going to be pointing this way towards positive x. If it's a negative number, it's going to be pointing that way, which is in the negative direction. Okay? Sorry, I'm going to erase this here, because I want to illustrate the difference between positive and negative numbers in terms of their magnitude and their direction. Okay? So let's say that we have the number 4, and then separately we have the number -2. These are just 2 examples that I'm coming up with on the fly. In one dimension, the number 4 is a vector whose magnitude is 4 and whose direction is to the right. Okay? Likewise, the number 2 would be a number whose magnitude is 2, but whose direction is to the left. Okay? So the magnitude is really the length of it. It kind of like speaks to the intensity of it, like how big or small, how fast or slow. When we move on to define vector fields in the next section on tangent spaces, that concept is going to really speak to why we're learning this in the context of differential equations, because the state equations define vectors that describe movement in the state space. Okay, so if I have the number 4 as a positive number, so its magnitude is 4, and its direction is to the right. I'm in 1D, so I'm stuck on the line, so I can only go right or left. Likewise, -2 has a magnitude. The magnitude of -2 is just 2. It doesn't include the negative sign, and in fact, magnitudes in general are always a positive value. In the case of one dimension, the magnitude is simply the absolute value of the number. And that's because the negative or positive sign in front of the number is to denote the direction. And so you can see that the vector arrow that I've illustrated for 2 is about half as long as the vector for 4, and it's pointing in the other direction because it's negative. So that's a new way to see a familiar concept of numbers, and then we're going to scale that up into a higher dimension. Right, numbers for higher dimensions, okay? Our next thing would be the concept of 2D, where we have a vector x comma y, and that's like the state spaces we were just talking about, where we have 2 state variables instead of 1. Now that we have x and y, instead of being stuck on the number line, we are going to live in the 2-dimensional plane. Right? And it sounds familiar. In my video about state spaces, I had examples of 1D, 2D, and 3D. Remember? And I talked through those. And 1D was the line. 2D is the plane. 3D is like this 3 space with 3 axes. And 4 and higher, those are really hard to visualize. But luckily, we have a theory of vectors. And we'll go further into the theory of what's called linear algebra, in which we can work with the higher dimensional spaces even though we're not able to visualize them. That's why we really need this powerful foundation of a general theory of higher dimensional space. Okay, so moving on to this, maybe I'll use some of my colored markers to illustrate a couple different vectors. Let's say that we have a vector that's maybe 4. Oh, sorry. I was writing them. So you can either write them vertically or horizontally. I'll stick to horizontal for now, but as we move on, hopefully you don't feel bad if you see this rotate into kind of a vertical format. So what I'm saying is you could either write it like this, or sometimes you'll see it written like that, where the x is on top of the y. Either way is fine for now. So let's say that I'll use this way. I have the number 4 minus 1. If this is my xy point, what that's going to look like is that I'm going to go over by 1, 2, 3, 4. I'm going to go over 4 in the x direction. And what I'm going to do is I'm going to go down by -1 in the y direction. And really, I bet you're like, yeah, I'm just plotting an xy point. I know how to do that, right? But what we want to layer on top of that is really focusing on the magnitude and direction of that vector. And so we're going to take a line and draw it from the origin. We're always going to draw our lines from the origin, and we're going to connect it to the end of that xy point that we plotted. then we can start to see that it has a direction. You see, it's kind of pointing this way. It also has a magnitude. What is the magnitude of this arrow? Like, what's the distance as the crow flies from here to here? Hopefully, you start to think back to your pre-calculus training, in which we learned about this probably when we were learning about tangents and sines and cosines, stuff like that. Pythagorean theorem. Remember the Pythagorean theorem? So the actual length of this vector is going to be the square root of 4 squared plus 1 squared, right? So we're going to use the Pythagorean theorem to say, what is the length of this hypotenuse? It's going to be the sum of the squares of the x component and the y component, and then we have to take the square root, right? I'm not going to write that on the board because we don't really need to take it that far right now. But hopefully that reminds you of some of the stuff from pre-calculus 2, which is the reason why that's a prerequisite for this. Right? So the magnitude, again, can be obtained by using the Pythagorean theorem. And then the direction, again, from pre-calculus, the direction is usually denoted as an angle theta, and how big that angle is coming off of the positive x-axis. That was the common way to define it in pre-calculus 2. So you're going to see that I've got kind of a negative little bit of a theta here. And again, I'm not going to write this on the board, but the value of theta would be the inverse tangent of the ratio of y over x. Remember from pre-calculus? Yeah, so the arctangent is involved in actually computing the angle. But for now, let's just focus on the visuals. Okay, so that's one example there. And then maybe as another example, we could look at the number maybe like -2, 3. Right? So a vector like that, -2, 3, would go -2 to the x, and it would go 1, 2, 3 up to the y, and it would go like this. Okay? And so again, it has a magnitude. We need the Pythagorean theorem to calculate that. And it has a direction, usually defined as the angle coming off of the positive x-axis, and when we need the arctangent to calculate that. Once we have these vectors in place, there are certain ways that we can manipulate them, and the two specific ways that are focused on, the two most important ways from section 1.3 are addition and scalar multiplication. Okay, so visually what addition is it's like doing going to the end of one vector and then layering the other vector on top, right? So if we wanted to do this plus this, we would go to the end of this vector first, and then we would go backwards by 2, and then we would go up by 3. So it looks like we would end up right here. I'll use another color for that. So if we wanted to add them, if we added them together, that plus that, if we add them together, we just have to make sure that we do apples to apples and oranges to oranges. Who knows? Maybe we're actually modeling apples and oranges, or tuna and sharks, or molecules A and B. No matter what we're modeling, the states, they have to stay in their own spot, okay? So if we have 4 tuna and -1 shark, that doesn't really make sense, but somebody owes me a shark. The 4 has to always stay on top, and then when we add them, you will only add components that are also in the top position. So when we add them here, we're going to do 4 minus 2. And likewise down here, the second component is called -1. The other second component is 3. So we're going to have -1 plus 3. And so we're going to get 2, 2. Now remember when I was just saying that's kind of like going to the end of one and then doing the instructions for the next one. So you see we're going to the end of this one, the end of the blue one, and then we're going, I'm going to go backwards by 2 in the x, and I'm going to go up by 3, 1, 2, 3, and I'm going to land right there. And that's the 0.22, which confirms the arithmetic that we've done on the side. It doesn't matter which one you start with. This would work just the same if we first went to the end of this vector. So we started at the end of minus 2, 3, and then we said, you know what? I'm going to go forward in the x direction by 4 because that's the x component of the blue one. So I'm going to go 1, 2, 3, 4. And then I'm going to go down by a y component of minus 1. And then I'm going to go down, and you see I land on that same exact spot. Also, if you check the week 2 schedule page, you'll see that I put a fun Desmos link in there that allows you to play with vector addition. So you can kind of see how that lines up. Scalar multiplication is the other thing that we want to focus on for vectors. And scalar multiplication means that you take a vector, like maybe the vector 4 minus 1, and you simply multiply it by a single number. Just one single number that is not a vector itself, it's just one number, is usually called a scalar. A one-dimensional vector, since that is just a number, a 1D vector is a scalar, but it's better to call it a scalar so that you know that it's just a single thing and it's not like trying to be a vector. Okay, so let's say that I want to multiply this by 3. Then I would just multiply each and every component separately by 3. So this would be 12 minus 3. Okay, and how to see that geometrically is that this blue vector here, 4 minus 1, what I'm saying when I multiply it by 3 is that I'm stretching it out to be 3 times as much as it used to be. And so when you're multiplying by a scalar, it actually influences the magnitude. It increases or decreases the magnitude by a factor of exactly what you're multiplying it by as a scalar. I don't have enough space to draw this on the board, but you can see it would get stretched out. Its direction would not change at all, but it would simply be elongated to be 3 times as long as it was. Okay, if you multiply it by a negative 3, though, watch what happens here. I'll emphasize it using a different color pen. If this was a negative 3, then negative 3 times 4 would be negative 12, and negative 3 times negative 1 would be positive 3. Okay, and so when you multiply by a scalar, that scalar, like we were saying, that one-dimensional vector, is only going to either be plus or minus. Its direction is either only going to be this way or that way. You multiply a vector by a negative scalar, what it does is it elongates it equivalently, but it also flips the direction to exactly the backwards direction of what it used to be. So if I multiply that blue vector by minus 3, then I have a minus 12 in the x, and I have a plus 3, and so I'm going to end up with a direction that's exactly 180 degrees, or pi radians, in the opposite direction of the original direction of the vector. Hopefully that clears up some questions related to vectors. I'm going to go back to the list now, see what's going on. But it didn't do the negative. Okay, great. I'm glad that I was able to clear up misunderstandings about negative scalar multiplication. And I didn't specify the book section, but I was referring to section 1.4. So now I'm going back to our brainstorm, looking for other ways that I can help you all out on your homework. The top winner here in the poll is 1.4.17, which I already did, though. And then we have further exercise 2 and further exercise 8 as being specifically named exercises. So let me check those out. And I'm assuming those refer to section 1.4 because it says, which exercise from 1.4 do you want to see? And so people are asking for number 2, which is a really important example about carrying capacity. And then we have number 8, which is a great example about kelp, sea urchins, and sea otters. Great, thanks for inputting those. So, further exercise 8, I feel like is winning the battle. Actually, for those who wanted to see a more explanation of logistic modeling, if you watch the YouTube live from this Tuesday, so the 4/7 YouTube live, you'll see that I actually did explain the logistic model a little bit in that live video. And so go ahead and look at the live video from Tuesday, just 2 days ago, to see a little bit on further exercise 2. But I'll go into further exercise 8 because it's much bigger. And yeah, let's talk about that one. It also has the most votes on there. Hopefully while I'm erasing the board, you're all flipping to page 45. Go to page 45 and look at further exercise 8. It's totally understandable if you haven't done that one yet, but it would be nice if we could all read it over so we're kind of aligned and we're on the same page. Yeah, turn to page 45. I like that some people started the abbreviation FE for further exercise. I'll have to adapt. I'm glad somebody thought that was funny. Me too. Me too. Thanks for the comments. I really appreciate those who are able to do the live chat on the side, so I don't feel like I'm just talking to myself so much when I do that fake laugh. So somebody got that. Yeah, FE is what I'll use for further exercise following off of the convention that you've all started. So we're going to do FE8 from 1.4. And that has kelp, urchins, and otters. Kelp, urchins, and otters. So it says here, for those who don't happen to have the text, kelp, sea urchins, and sea otters form a food chain off the coast of Northern California. Use the following assumptions to write a differential equation model of the food chain. And then they give you this long list of stuff. And we're supposed to fold all that into a set of state equations. How many state equations are we going to have? Hold on, I need some water. Don't worry, I'm okay. Just swallowed some spit. Okay, that's right. 3 equations. Yeah, we're going to have 3 state equations for each of those 3 state variables, K, U, and O. So we're going to have K prime, U prime, and O prime. So we'll go down the list of these bullets and see how that affects each of these things. The first bullet here says that kelp grows at a per biomass, which is like per capita rate of 0.02. Per capita rate. Do you remember that per capita rate? That's actually another one of the things that I have in the concept quiz there. Let me write that on the board. That's very important. A per capita rate is a rate just like the rates we have described over there, but per capita. So it's a rate divided by the number of members. Okay? And so, for example, for kelp, that would be K divided by K, that would be K prime divided by K. That's what the word per capita means, is it means what's the rate? So the rate is K prime, and then the per capita part is per is divided, and then capita is how many of them we have. Okay? So when it says the per capita rate is 0.02, that means that this is equal to 0.02. Does that have any feedback? When I write it like this, it might look like it doesn't because I've been emphasizing that when the right-hand side of a state equation doesn't have a variable, there's no feedback. But you got to watch out. This is not a state equation. This is a statement of per capita behavior. In order to go back to the state equation over here, we have to make it so just the k prime is on the left-hand side. And so how we're going to do that to this is we're going to multiply both sides by k. And so what that transforms into is a statement that state equation k prime is equal to 0.2 times k. So you're going to see that that does have feedback. It has positive feedback because this is a positive number, just a little bit of positive feedback. And that's the term that we're going to fold in from the first bullet right into this equation right here. All right. So that's the first part there. Yeah, I know. I'm a little scared when people cough too. That's why I was just letting you know that it was just a little spit. The second bullet here says that due to shading, kelp dies at a per biomass rate, again, that's a per capita rate, proportional to the amount of kelp with a proportionality constant of 0.1. Okay, so this over here was the birth rate. But then the next bullet, the second bullet, says that we also have kind of a death rate associated, and it's also a per capita rate of k prime over k is equal to 0.01. So this is the birth rate right here, and this is the death rate, what they call the death rate. Birth rates are always positive because it increases the population. And likewise, death rates should always have a negative in front of them because it's removing members from the population. And so I have to put a minus here. And just like I did before, I would multiply both sides by k so that I can see that this is actually a form of negative feedback. And really, the full equation for the state of k, how k is changing, is going to be a sum of all these terms that we're building up. So I'm just building up the terms on that side of the board, but really over here, we have to fold them all together. And so if you wanted to use algebra and sum these together, it seems like that we have, when we combine births and deaths together, we have overall a per capita growth rate, because it's positive, the sum, of 0.01. I won't combine the terms right now, though, so that you can see how each one of these terms came from a different place. But if I was really doing modeling, after I wrote down all these equations, I would try to combine like terms using algebra as much as possible so that it would simplify the statement of my model. Okay, so the next thing that it says here is sea urchins eat kelp. A single sea urchin consumes kelp at a rate of 0.05 per month. Okay, a single sea urchin consumes kelp at a rate of 0.05. So urchins, I'll say that's really important that they said a single urchin. That's going to be important for how we're going to fold it into the overall model. So a single urchin eats kelp at a fixed rate It's really nice to start to see a unit on some of these rates, because that gives us an idea of what the units for the time variable are. So when it says that per month, that makes me assume that the underlying time dynamics is happening on the time scale of months, that the independent variable time is in units of months. As we move on to the next chapter in calculus, you'll see really what k prime is, and really what all of these primes are actually an instantaneous derivative. So this is really dk dt. And likewise, the other equations are going to be du dt and do dt. That's kind of a look ahead to the next chapter. But I wanted to emphasize it at this point because when you see this number per month, that has to do with the per divided by, and then the t, the rate of change with respect to time, which is in months. Okay, let's see what we can do about this. A single urchin eats kelp at a rate of 0.5 per month. So what it's saying there is it's speaking to the effect of a sea urchin on the population of kelp. The urchin is pulling members out of the kelp population. A single urchin, so here I'm going to go to the kelp rate of change because the statement on the third bullet is a statement about what's happening when you remove kelp members. So it's getting removed at this rate. But that's the single urchin, right? And so how is this affecting the overall kelp population? We're going to have to multiply this by the number of urchins. And so that's why I have a 0.5 minus u there. A lot of times in these models, it says that consumption is proportional to the number of members of a population. And so I'm surprised that it doesn't say that the sea urchin is consuming kelp at a rate that's proportional to the amount of kelp. If it did say that it was proportional, that the consumption was proportional to the amount of kelp, then I would have also added a k, a multiplier k here, but it doesn't say that. So I'm not going to do that. I'm just going to leave it as multiplied by u, and that's because we have to say that this is a per individual urchin. So how much kelp is getting pulled out times by how many urchins there are. Okay, then it says the sea urchin birth rate is proportional to the amount of kelp that the urchins consume, which we just derived right here, and then with a proportionality constant of 0.2. Okay, so it says that the birth rate is proportional to the food consumed. Here's the amount of food consumed right here, 0.05 u. You'll notice that I put that as a positive because it's positively affecting the urchins and it's negatively affecting the kelps. So I took this term and moved it over here in the positive sense, but then it says that it's proportional to the amount of kelp consumed with a constant of 0.2 in front. So I also need a 0.2 multiplying that in front. Again, before I start to actually work with this model, I would definitely multiply the numbers 0.2 and 0.05 together to simplify the expression. But I won't do that right here because I'm trying to show you how all these things are getting derived from a statement of the words. So that's why I haven't multiplied it out. Sea urchins die of natural causes at a per capita rate of 0.01. So that's their death rate. We kind of went over that before. And at 0.01, and I'm multiplying it by u because per capita rate. We kind of went through that before, but it's the same reasoning about the per capita rate for kelp over there. And in fact, it's the same constant of proportionality as well. The rate at which a single sea otter eats sea urchins is proportional to the sea urchin population with a proportionality constant of 0.3. Okay, we're on the third to the last bullet here. We're on the 1, 2, 3, 4, 5. We're on the sixth bullet of question 8 here. And this is trying to tell us how many urchins are getting pulled out of the urchin population due to the otters eating them. So what I'm going to do with this statement here on the sixth bullet is I'm going to be taking it away from the urchin population, and it's going to be proportional to the sea urchin population, 03 here. Hold on, I'm going to run out of space. Okay, this 0.03 is coming from the sixth bullet there, and it says that It's proportional to the sea urchin population. So that's why I put a U there. And it also says the rate at which a single otter eats. Remember when it said about a single urchin eating kelp? And so we had to take this statement over here and multiply it by the population. So this is a single otter eating urchins. So in order to describe the whole population of otters eating urchins, we're going to multiply it by an O. And there you have the familiar U times O, which is just like chemical kinetics where we had the A times B, the familiar description of interaction as a product of the two interacting populations involved. That's very common in ecological models and also chemical kinetic models. Second to last bullet now, it says the sea otter birth population is proportional to the amount of sea urchins that the otters consume, but then with another proportionality constant of 0.01. And so just like when I took this piece and I folded it into here, and then they gave me another constant, same thing as we move on to the next stage in the food chain, is I'm going to take this piece here, and I'm going to fold it into this population in the positive sense, and then I'm also going to multiply it by the proportionality constant that they're stating. So that's why I have this. That's where I get this long statement right here. It's that piece from the urchins going out into the mouths of the otters, and then the proportionality constant. Finally, we have that sea otters die at a per capita rate of 0.001. And so that's why we have this term right here, and that was a per capita rate, and so we had to multiply it by the number of otters. That concludes question 8. That was quite a doozy. I've got one more comment to look at. Let's see, it says, I also had that problem with does the 0.05 mean per urchin per kelp or just per urchin? Yeah, but that would mean that urchins eat kelp when it doesn't exist. I love that question. Thank you for putting that in, because I feel almost like it was a typo in the question. Like, I really am feeling you. A student here, I'll repeat it again, has said, I also had that problem with the 0.05 per urchin per kelp. First, I came up with the same thing, 0.05, but it would mean that urchins eat kelp even when the kelp doesn't exist because it doesn't have the K. And it would also result in a U prime is equal to minus 0.03 UO, which also feels wrong. I'm not sure what that second part means. Maybe you could elaborate on that second statement that you added, but the first statement here is very important, and it's a very astute observation that how could urchins be eating kelp if they don't see any kelp? So really, I honestly feel like there should be a K here, and I feel like that same K should be here. Anytime we model interactions, it is proportional to the product of the two populations involved. And I think that maybe that just could have been described with a little more specificity in the third bullet. And the third bullet, when it says a single urchin consumes kelp at a rate of 0.5 per month, I would have preferred to say a single sea urchin consumes kelp at a rate proportional to the kelp amount, at a rate that's proportional to the biomass of kelp with a proportionality constant of 0.05. That's the kind of statement that I would have written for the third bullet that would have resulted in this correction that I've done in red here. So I'm not really sure if that was, if that's what he meant, or if that was a typo, or what he really means is that it's just a constant rate. That's kind of an open question in my mind, and thank you for elaborating and bringing us back to that in the question. So I see some other people adding comments that say the urchin population would always be decreasing and never increasing. And kelp forests are attacked by urchins and endanger ecosystems based on the forest. Yeah, so they can't be eating kelp if there's no kelp around. So really, we do have to have that K in there. I'm a little bit over time here, and I do have actually an appointment I was supposed to be at 2, so I'm a little late, and sorry, I'm going to have to cut it off. But thank you, everybody, for being here and watching this. I hope this was really helpful. And maybe there weren't so many questions because you haven't reached those questions in the assignment yet. But your next resource is going to be the homework discussion board. And so please now bring all questions to the homework discussion board. And I'll be watching those carefully too. And so will the math TAs. And we'll try to give you as much help as we can in anticipation of the due date on Sunday night. Thanks, everybody, for being here. I'll see you later.